module we will continue discussion of analysis of a step voltage on a transmission line using lattice or bounce diagram. So, I hope this particular slide should be familiar to you if you have seen the last module. We had a transmission line excited by a step voltage by a source of amplitude V0 connected through with it, the source had an internal impedance of Rs or internal resistance Rs connected to the load via a transmission line of length L and propagation velocity V. So, therefore, the total delay in this transmission line was Td. Okay. So, what we were discussing is that at t equal to 0 when the switch is closed and this step voltage appears on the transmission line, the voltage source does not really see RL. It is like this. You imagine that there is at a very large distance there is some object which is glowing. Okay. For example, a star is glowing, and then when you see the light from the star, it is actually not the light that you are seeing which is just left the star's surface. What you are actually seeing is that light which actually left the star millions and millions of years ago, because that time delay is the factor over there. Okay. So, the light which just leaves the star surface today, or the surface from the earth today, if you were to shine a very high power laser beam, does not immediately see its load which may be located millions of miles away. What it sees is that the first time when you launch this light, it will see the atmosphere, whatever the equivalent impedance that the atmosphere presents is the impedance that we will see, okay, that the light will see. So, in the same way RL becomes visible after the voltage is actually crossed over and spent time to reach RL, and even then it will not be visible, it will actually have to come back. Okay. So, until 2 time Td the source does not really see the effect of load. This is like a radar thing. Okay. You take a pulse, you throw a pulse at a distance, until the 2 times the propagation delay is finished, you will not be able to receive that pulse back. Okay. And only when you receive the pulse back you have some idea of what is the target there. So, in the same manner this is essentially the idea, the pulse will not, or the step voltage will not see this load RL, but instead it sees the transmission line R0 as its immediate impedance, and that creates a voltage divider which is the voltage that is launched, and the voltage across that R0 is the voltage that is launched on the transmission line. Okay. So, with an amplitude of V1 plus given by R0 plus Rs will be launched on the transmission line. We represent that by writing this as V1 plus. Okay. So, we represent that one by writing here as V1 plus as the initial voltage that is launched on the transmission line. Okay. So, at the receiver when you, or at the load side when this time delay of Td is elapsed, okay, right, there is a time delay of Td. So, on the time axis this is 0, but this is Td. Okay. So, at time Td the initial voltage V1 plus from the source appears, but immediately as soon as it reaches the load there would be a reflection created, and that reflected load will be equal to, sorry, the reflected voltage will be equal to gamma L times V1 plus, where gamma L is ZL or RL minus R0 by RL plus R0. Okay. So, that voltage is reflected back and then begins to travel from the load to the source side. What would be the total voltage on the load side? It would be the sum of incident and reflected voltage. Incident voltage is V1 plus, reflected voltage is V1 minus, the sum is actually equal to 1 plus gamma L into V1 minus. That would be the voltage that is seen on the source side. So, if you were to, for example, put an oscilloscope here, okay, so you put an oscilloscope here, you would see that there is nothing happening until time Td, right, and at that point you will see a voltage which is 1 plus gamma L into V1 plus. Okay. So, this is the voltage at load side. Okay. This is as a function of time that we plot. Okay. Similarly, as I was saying, you can put an oscilloscope in the middle of the transmission line. So, V at Z is equal to L by 2V, that is V at Z equal to L by 2. So, at this halfway distance, right, until some half time Td by 2, because it will take if it takes 1 Td to reach from the source to the load side, then it will take Td by 2 to reach halfway through across the transmission line. So, until that point there is no voltage, thereafter the voltage will jump. This can be obtained by actually drawing a straight line and then following it up, where it intersects, that is the point where you actually start seeing the voltage. So, this is how the voltage waveforms look halfway and at the load point. Okay. Now, this voltage which is actually beginning to go backwards, right. So, this V1 minus which is going backwards would actually reach the load, reach the source, and at that point if gamma g happens to be equal to 0, then this would be absorbed. There won't be anything that is going back now. Once if gamma g is equal to 0, this voltage would be absorbed and this would be the end of all the voltages. The load voltage continues to remain at 1 plus gamma L V1 plus, and then the source voltage would actually receive whatever the voltage that has been sent plus this voltage gamma L V1 plus, and then it would actually stop. There is nothing out there that is happening. However, if gamma g is not equal to 0, as in case when Rg is not equal to R0, this would act like an incident voltage on the transmission line and create a next voltage which is reflected from the source, which would then travel again in the same direction as the initial V1 plus. It would travel from source to the load. Okay. What would be the amplitude of this voltage? Well, this voltage amplitude is gamma g times gamma L V1 plus, because gamma g times V1 minus is the reflected voltage, but V1 minus is gamma L into V1 plus. Therefore, this would be gamma g gamma L V1 plus. This is the voltage that is going backwards. Now, at this point there would again be a reflection, right. This reflected voltage will have an amplitude of gamma L gamma g gamma L V1 plus, and this cycle continues. Okay. What is the voltage here on the, what is the next bit of the voltage here? This is gamma g gamma L V1 plus gamma L and so on. Okay. So, the total voltage, the steady state voltage would actually be the sum of all these individual voltages. Okay. So, you can actually do that sum. So, probably a better way to understand this one or to get more intuition on this particular technique is to actually take an example and solve it. So, let us look at this example. I have the source impedance which is 25 ohms, okay, and I have a source which is essentially a step voltage of amplitude 10 volts which I am going to connect at t equal to 0. So, this is the switch at t equal to 0 and connected to a transmission line such that the delay is 1 milliseconds. Okay. So, here we do not have to bother what is the length and the propagation, we just assume that the transmission line has a delay of 1 milliseconds which we have calculated by other means. Z0 or R0 of the transmission line is 50 ohms and we connect a load which is say RL of 100 ohms. Now, we want to find out the voltage at the load side, voltage at the source side, voltage in the middle of the transmission line. How do we do that? First step, okay, calculate gamma L. Gamma L is 100 minus 50 by 100 plus 50 which is 1 by 3. Calculate as a second step what is gamma G. So, you are in bad luck because gamma L is not 0, there will be reflections. What is gamma G? Is that 0? Unfortunately no, gamma G is 25 minus 50 divided by 25 plus 50 which is minus 1 by 3. So, what you see is that gamma L and gamma G are equal in magnitude, but they are not equal in sign. So, there is also the fact that gamma G is also not 0, there will be reflections, multiple reflections on the transmission line. Okay. The third step is to actually calculate what is V1 plus. This is the initial voltage amplitude that is launched on the transmission line. To calculate this one, you need to form a voltage divider between Rg and R0, right, and whatever the initial voltage source, whatever the voltage source that you have, and this gives you 50 by 75 into 10 which is 20 by 3 volts. Okay. So, let us actually change this one from 10 volts to 9 volts just to get some initial real nice numbers. So, what we get here is 50 by 75 into 9 which is say 2 by 3 into 9, or this is 6 volts. Okay. So, this is the initial voltage that we are launching on the transmission line. Now, you draw the bounce diagram. Okay. So, this is my bounce diagram which I am drawing, okay, and I can normalize this one with respect to TD. Therefore, this would be 0 time, 1 millisecond or 1 time delay, 2 time delay, 3, 4, 5, 6 and so on. Okay. Here also the same thing, 1, 2, 3, 4, 5 and 6. So, this is the source side. Okay. Write down gamma G is equal to minus 1 by 3, write down on the load side gamma L is equal to 1 by 3. Okay. Now, you begin moving the voltages. So, initially the voltage that would be launched will be 6 volts and it would propagate like this. So, this is 6 volts, okay, and then right after this 6 volt reaches there will be reflection. So, the reflected voltage V1 minus is equal to V1 plus into gamma L which is 6 into 1 by 3 which is 2 volt, right. So, a 2 volt is actually launched back. So, you can write this as 2 volt, okay, and this is 6 volt. So, what would be the total voltage at this point? The total voltage will be 6 plus 2, which is equal to 8 volts. Okay. So, the voltage actually jumps up to 8 volts at t equal to 1 millisecond. Now, this 2 volts has come back. What would be the reflected voltage? Well, the reflected voltage will be 2 times. So, this would be V2 plus will be gamma G into V1 minus, which is minus 1 by 3 into 2, which is minus 2 by 3 volts. Okay. So, a minus 2 by 3 volts is launched towards this side. So, minus 2 by 3 volts is launched. What would be the voltage reflected from the load side again? This would be V2 minus will be gamma L times V2 plus, right. Gamma L is 1 by 3 and V2 plus is, we have seen, minus 2 by 3, therefore, this is equal to minus 2 by 9 volts. Okay. So, this would be minus 2 by 9 volts. So, minus 2 by 9 volt. So, further reflected voltage will be minus into minus will become plus. So, 2 by 9 into 1 by 3. So, that would be 2 by 27. So, you can see that the amplitude of the reflected voltages keeps on decreasing, and for 2 by 27 or something we can probably stop at this particular point. Now, let us try to sketch the waveforms. Okay. So, let us try to sketch the waveform here first at the load side. Okay. So, at the load side in terms of time, okay, normalized with respect to the time delay of the circuit, I am trying to plot the load voltage. Okay. So, how does it look? Initially at up to time t is equal to 1 time delay, which is 1 milliseconds, there will not be any voltage. So, at 1 you actually see a total voltage of 6 plus 2, which is 8 volts. Okay. So, this is 8 volts and this would continue to remain until the second voltage waveform reaches here, that is until this minus 2 by 3 volts, which is 2V2 plus, reaches this load side at 3 milliseconds, right. So, at 3 milliseconds what would be the total voltage? Whatever the initial voltage that is there plus the voltage that is now here. So, this would be minus 2 by 3 plus minus 2 by 9. Okay. So, this is minus of 2 by, so 2 into 3 you can do, and this would be 9 plus 2 by 9, right. So, this would be 6 plus 2, this is around minus 8 by 9. So, approximately minus 1 volt. So, the voltage actually drops now 8. So, the total voltage is 8 minus 8 by 9, which is approximately 8 minus 1 volt, this is about 0.9 or something. So, this is roughly 7 volts. Okay. So, I am not really interested in writing down that one. So, you can actually do all these calculations. 8 minus 8 by 9 volts is this voltage, and this change happens at 3 milliseconds. Okay. Now, again at 5 milliseconds something must happen, right. So, let us write this one, this is 8 minus 8 by 9 volts. Okay. So, at 5 milliseconds you now get this 2 by 27, and then there would be one more voltage that has gone back. So, there is actually a positive voltages up there. So, the voltage actually just slightly increases. Okay. It would actually increase very by a very small amount. Okay. And this will again decrease further, and it would again increase further slightly, and then eventually reach a steady state. Okay. What would be the steady state voltage? Under the steady state condition, the transmission line can be removed and the voltage simply becomes 100 divided by 25 plus 100 into 9 volts, which is 100 by 125 into 9 volts. This would be the steady state voltage at the load side. Okay. So, you can convince yourself by plotting this particular thing. Also, if you look at the way this voltage is there, you can imagine that there is some sort of a underdamped circuit, right. So, if you look at the underdamped amplitude oscillations, it would look like this, it would go up, come down, go up, come down, and this is the underdamped circuit that one might think. Okay. There is a slightly different circuit, okay, we will see that one later, which would look like an overdamped circuit. Okay. This was how we could draw the voltage waveform at the load side, but what if I want to find the voltage at midway through here, right. All I have to do is keep moving along this line until I hit the corresponding line, okay, carrying a voltage, and keep adding that one. Okay. So, at this point the voltage is 6 volts, then when I hit here it would be 6 plus 2 volts, that is 8 volts, then I come here, that would be 8 minus 2 by 3 volts, then it would be 8 minus 2 by 3 minus 2 by 9 and so on. Okay. So, if you were to plot the voltage waveform as a function of time at z equal to L by 2, that is halfway through the transmission line, initially until Td by 2, that is until 0.5 you do not see anything. So, at 0.5 you see 6 volts, okay. Then it will again change at 1.5 milliseconds or 1.5 time durations, at which point it would again rise slightly because this is 2 volt jump. So, this becomes 8 volt. Then again at 2.5 this would drop somewhat because there is minus 2 by 3. So, it is 8 minus 2 by 3, and then at 3.5 again this would drop a little bit because now this would be 8 minus 2 by 3 minus 2 by 9 and so on. So, here it would again rise and then eventually do something like this. Now, at the source side what would happen? Initially there is a 6 volt that is launched. So, at the source side if you were to draw, again normalizing T with respect to Td. So, this is V at Z equal to 0, which is the source side voltage that we are drawing. So, immediately as the switch is closed, a 6 volts is launched. Thereafter at 2 milliseconds, that is after 2 time delay, the voltage actually changes over from 6 to 6 plus 2 minus 2 by 3, which is 8 minus 2 by 3. So, now it would actually change over to 8 minus 2 by 3. So, whatever that voltage is, right. So, that would be the voltage here, and then it would again change over, right. So, I do not know whether this is minus or plus, does not matter, but this is how you would actually calculate. Okay. So, this is one of the circuits which I wanted to show you how to do lattice analysis or bounce diagram. For completeness sake, let me also consider a case where I have a step voltage waveform, okay, connected through an internal impedance of say Rs is equal to 100 ohms, and then I have a transmission line which is R0 of 50 ohms, and then I also have R L which is 100 ohms. So, in this case clearly gamma L happens to be 1 by 3, gamma G also happens to be 1 by 3. So, here the voltages seem to be having only positive reflection coefficients, and that shows up when you draw the bounce diagram. So, you draw the bounce diagram again by normalizing T with respect to Td, okay. Again assume that this is 9 volts, okay. So, with 9 volts the initial voltage that is launched will now of course be different. The initial voltage launched V1 plus will be 50 by 150 into 9 volts. Oh well, not really. So, this is 2 by 3 into 9. So, this is 6 volts launched again. So, 6 volt goes through, okay, at T equal to 1 or T by Td is equal to 1, it reaches here. At this point 6 into 1 by 3, which is 2 volt is launched back. So, this is 2 by 3 volts. At this point again, so this is at time T equal to 2. So, at this point or at this time again 2 by 3 into 1 by 3, which is 2 by 9 volts is launched. So, this is 2 by 9, and then this again is launched as 2 by 27 and so on. Okay. Now, if you were to write down what is the waveform for load, you will see that the load voltage actually goes something like this. So, at T equal to 1 time delay, the voltage at this point jumps up to 6 volts, then at 3 the voltage again jumps up. So, this would be 6 plus 2 by 3, okay. So, this is 6 volts launched, and then 6 by 3, sorry I made a small mistake over here, this would actually be 6 into 1 by 3, which is 2 volts launched here, and then 2 by 3 is launched back again at this point, and then from 2 by 3 you launch again 2 by 9 over here. So, this is 2 by 9. So, initially the voltage will be 8 volts because it is 6 plus 2. So, it is 8 volt that is there at T equal to 1. Then at T equal to 3 you have 8 volts already. So, this is already 8 volts plus 2 by 3 plus 2 by 9, that is the voltage that you need to add to this 8 by 8 volts, right. So, it would actually jump up, okay. Then again once more when you get these reflection things, it would again jump up slowly, okay. So, this way it would keep on doing until it basically reaches the steady state. So, you can see the response difference in that this response keeps on growing until it reaches the steady state as some sort of a overdamped circuit, okay. So, this is an overdamped circuit, okay. Do not take these words too seriously, these are just kind of an analogy with control system because the waveforms look like that. This is an underdamped circuit because the waveform was actually oscillatory, okay. to get oscillatory waveforms, you either need gamma g to be negative or gamma L to be negative. If both gamma g and gamma L are positive, then you get an overdamped kind of a response. So we will close our discussion of transients on transmission lines with this example. We will talk about capacitive termination of a transmission line in the next module.